All right, so chapter 4 is starting off our trig section. We're going to talk about primarily with chapter 4, we're going to talk about the basics of angles and things like that. And then we're going to get into more advanced parts of trig. So first of all, let's go back to geometry, basic geometry, and talk about an angle. The hour hand of a clock suggests a ray, a part of a line that has only one endpoint and extends forever in the opposite direction. An angle is formed by two rays that have a common endpoint. One ray is called the initial side, and the other is called the terminal side. So here we have the initial side, and then we measure theta through to get to the terminal side. Remember, when we talk about an angle, we're talking about movement of one line through an arc to get to another position. So when we talk about an angle, we're actually talking about this part right here, the measure of that angle. How far did that thing have to swing around this vertex B to get there? An angle is in standard position, very important because we'll talk primarily about angles that are in standard position. And standard position means that its vertex is at the origin of the rectangular coordinate system. In other words, it's at 0, 0. And its initial side lies along the positive x-axis. Those are the two requirements for an angle to be in standard position. So here are two angles that are in standard position. Here we've got alpha, that's what that symbol is, and we were in standard position, vertex is at the origin, initial side is along the positive x-axis, and it swings through to get to there, to the terminal side. Now, this is a situation where alpha is positive. We're going to measure angles on the coordinate plane, counterclockwise being positive angles, and clockwise, like theta is over here, being a negative angle. So starting here and sweeping back this way, we're going to get a negative angle. Now, if our terminal side ends up on one of our axes, positive y, negative x, negative y, or even back to positive x, then that angle beta, that's the sign for beta, is going to be what's called a quadrantal angle. Now, if we measure angles using degrees, we have descriptions of different angles. You should already know these, but just to kind of reiterate and make sure and remind you here, an acute angle is an angle that is between 0 degrees and 90 degrees. It does not include 0, it does not include 90. Notice the symbols here. A right angle is exactly 90 degrees. An obtuse angle is an angle between 90 degrees and 180. Notice does not include those two. And if it is 180 degrees, it is called a straight angle. Now, we'll be using notations such as theta equals 60 degrees to refer to an angle theta whose measure is 60 degrees. If you'll remember back in geometry, you would have written measure of angle theta equals 60, but we're going to shorten that down just a little bit and write it as theta equals 60. We also refer to an angle of 60 degrees or a 60-degree angle rather than using the more precise but a little longer and cumbersome phrase, an angle whose measure is 60 degrees. So that's the correct way to say it, and that's the correct meaning, but we're going to shorten that down just a little bit just so discussing it is not quite as much of a pain. All right, now, another way to measure angles is a radian, and that's going to be our transition. We're going to transition away from degrees and into radians because in the mathematics that are going to come after pre-cal, you're primarily going to use radian. Now there are applied math courses where you're still going to use degrees and things like this, but radian measure is a much more friendly, once you know what it is, way of dealing with it. Because radian, and you're going to find out through the definition, is based off of the circle itself. 1 radian is the measure of the central angle of a circle that intercepts an arc equal in length to the radius of the circle. So right here we have 1 radian. The reason we know this is 1 radian is because this circle right here, we have an angle that is intercepting an arc that is the same length as the radius. If we were to cut this piece or this curved piece right here out and stretch it out, it would have the same length as this right here. So that is 1 radian. Now what we end up finding is that there are 3.1415926 radians to go all the way around the circle. So that would be this angle, and it would be that would be what the radian measure would be to go all the way around the circle. Now notice the little note down here. It says for a 1 radian angle, the intercepted arc and the radius are equal. So that's just taking the opposite of this. So if we know that this is 1 radian, that means this arc length is equal to the radius of the circle. Now consider an arc length S on a circle of radius R. The measure of the central angle theta that intercepts the arc length is theta equals S over R radians, where S is the arc length, R is the radius, and theta is the central angle. Now, not only can we do that, but we can also work backwards, or work just a little bit of math here, and say that S equals, and we just multiply both sides by R, and we have R times theta as long as theta is in radians. And we're going to see this in just a second, but I wanted you to see where it comes from. Now, in all these, remember, the theta, our angle, must be in radians. It does not work for degrees. Now, the reason it doesn't work for degrees is, as we talked on the last slide, radians is based off of the circle itself. Where do we get degrees? Well, degrees come from the circle, and we split it up into 360 degrees. Well, where does 360 come from? Well, at one time, they actually thought that the sun went around the earth, and it took 360 days for that to happen. So a degree was the amount of sway through the sky, or how far around the earth it traveled in one day. Now, of course, we know now it's 364 1/4, or 365 1/4, so it's not. Can you imagine if they had known exactly how many? Can you imagine splitting a circle up into 365 1/4 degrees? But that's where 360 comes from, just a rough estimate of how long it took for, I don't remember if it was the earth going around the sun with the thought that they were doing, or the sun around the earth, but either way, that's how it ended up being. That's how it ended up being 360. It's a man-made measurement. It's not something that's based off the circle itself. So that's why it gets clunky when we start trying to do more advanced stuff, because it's just man-made introduction of a piece of information. Now, a central angle theta in a circle of radius 6 intercepts an arc of length 15 inches. What is the radian measure of theta? So to find that, we know we've got theta equals S divided by R, as long as our theta, and our theta would be in radians there. So when we put all our information in, the arc length of 15 inches and a radius of 6 inches, And here's the thing, I want you to notice something. What happens with our units? Inches divided by inches, those are going to cancel out. Radian actually has no, radian is actually not a unit. It's a ratio. So when we talk about radians, there actually is no unit attached. It's just that it's measured in radians. It's not actually a length of inches or centimeters or degrees or anything like that. It's just the ratio of arc length to radius. So our degrees, our units actually cancel out. So here we can simplify this. 3 will go into both of those, so we'll end up with 5 over 2 and radians. Now once again, we write radians, but radians is not actually a unit. It's just telling us what this measurement is. I don't know how. I really don't, it's kind of weird to have some measurement that's not in a unit, but there is not a unit that's attached to radians. Radians is the measurement, but it kind of goes, the thing is, it goes away in calculations like it's not there. That's the thing when you do applied problems. All right, now the relationship between degrees and radians. How can we obtain a relationship between degrees and radians? Well, we can compare the number of degrees and the number of radians in one complete rotation. And then once we know that, and we know that 360 is the amount of rotation of a ray back onto itself, all the way around, the length of the intercepted arc is equal to the circumference of the circle. Thus, the radian measure of this angle, central angle, is the circumference of the circle divided by the circle's radius r. In other words, the circumference of the circle of radius r is 2 pi r. When we cancel the r's out, we find that the theta for one circle's circumference is 2 pi. Now, because one complete rotation measures 360 degrees, or 2 pi radians, the same thing, they have to be equal, and if they're equal, then we can simplify that down, and 180 degrees equals pi radians. So these are two things that are equal, just different units. And I know I keep saying that, but radians has no unit. But they're measuring the same thing is the point. And they are the same measure. So if those two things are equal, then to change it, we can change one from one to the other, we can use this identity. So to convert degrees to radians, you're going to multiply degrees by pi radians over 180. So what happens is this, and I'll show you down here. If we have 45 degrees, we're going to multiply that times pi radians over 180 degrees, and what do you notice about the degrees? Well, if we multiply, or if we divide by degrees, they're going to cancel out. And that's the thing with this. And then to convert radians to degrees, we're going to multiply our radian measure by 180 degrees over pi radians. So let's say we've got 3 pi over 2. Now we're going to multiply that by 180 degrees over pi radians. So once again here, and radians, remember, is not really a unit, but the pi's are going to cancel out. They will not always cancel out. Sometimes you'll actually have a pi in your degree measure because there wasn't a pi to begin with. So your degree measure is not always going to be separate from pi. Sometimes it'll still have one in there. In this case, it cancels out. But more specifically, you've got a degree on top. So when we multiply this times the degrees, we're actually converting it into degrees. So that's how you would go about doing that. All right, so let's do a couple of these. Convert each angle to degrees in radians. So if we did 30 degrees, and I'm going to use a little table here. You may have seen these in chemistry. I like using the table. We want to get rid of degrees, so I'm going to put 180 degrees down here, and then pi radians here. So right here we essentially have a value of 1. They're just not in the same measure style. And I'm even going to get rid of my radians. So if you do this, the degrees of course are going to cancel out, and you're going to have 30 over 80, which is 1 over 6 times pi. So you end up with pi over 6. So 30 degrees is pi over 6 radians. Now, I'm going to skip the 90 because you did it right here, and 90 over 180 is just, 1/2, so you can get pi over 2 from that. Negative does not make a difference. We can still do it with a negative. So let's do negative 135 degrees pi radians over 180, more specifically the fact that these are going to cancel out. And you end up with negative 135 pi over 180. And then all you have to do is just reduce that. 135 is 45 times 3. 45 will go into 180 4 times. So we end up with what, negative 3 pi over 4? And that's all there is to it, to go from degrees to radians. Now, if you're going to go from radians to degrees, it's not that much different. So let's do pi over 3. I'm just going to continue that on out. And you don't have to use this table if you aren't familiar with it or anything. I just like to keep things separated. And we're going to end up with 180 on top this time because we want to go to degrees. And we're going to end up with pi radians on the bottom. So my pi's are going to cancel out. I'm going to end up with 180 degrees over 3. 180 divided by 3 gives me 60 degrees. All right, and I want to show you, this one's going to be the same as it was with the negative one. You just tag the negative along. But I want to show you this one specifically. So we've got 1 radian. And we're going to change it to degrees, so we're going to do 180 degrees over pi radians. Now, so you got radians here, and they're going to cancel out, even though radians actually is not a unit, blah, 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 I know that. So we end up with 180 over pi degrees. And you don't have to write it that way. That's just a weird way. I don't even know why I wrote it that way. But anyway, it's 180 degrees over pi. So there's one of those instances where even though you're converting it back to degrees, pi is going to tag along anyway. There are situations where that's going to happen if there was not a pi in your radian measurement. So just because the pi doesn't go away doesn't mean that you're not correct. Just understand that. All right, now to draw angles in standard position, you're going to start with putting your vertex at the origin. You're going to draw your initial side along the positive x-axis. Then you're going to sweep counterclockwise for a positive angle, clockwise for a negative angle. And here are just some examples. 1 whole revolution, 3 pi over 2, pi, and pi over 2. Now, one of the things that you're going to need to know eventually is what quadrant this thing is, and we'll deal with why you need to know that later. I want you to think about it though now. Let's say you're given an angle of 3 pi over 4 and you need to find out what quadrant that's in. Use these ideas right here. This is pi over 2. This is pi. This is 3 pi over 2. And this is 2 pi and 0. Ignore the pi. A lot of people get thrown off by the pi. Just think about the fraction. Where would 3/4 be? Would it be between 0 and 1/2? Would it be between 1/2 and 1? Between 1 and 1 1/2? Or between 1 1/2 and 2? Well, 3 pi over 4 or 3/4 will be between 1/2 and pi. So that would be over here in quadrant 2. So use the fractions and just kind of ignore the pi in your brain as you're thinking through this, and remember what these fractions are, and you can place wherever that thing is going to be. That's a good way to find where it's going to be, in which quadrant it's going to be. And if you're talking negative, you can just count backwards. Negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. All right, now more specifically, we're not really going to draw all these. You can figure out how to do it. Figure out what quadrant it's in first, and then just draw one in that general area. But more specifically, I wanted you to see these angles. And the question often comes up, well, why are we using these crazy things right here? Typically, when you have a Greek letter, you're talking about an angle. That's just one of the things that mathematicians have done over the years, and it's kind of become one of the things that's just understood. Generally, it's not always, but generally when you're describing an angle, you're going to use one of the lowercase Greek letters. And here are some of the ones that you're going to use more than not. More often than anything, you're going to see theta. If you see more than one, they're typically going to throw in alpha and beta. And then if they have quite a few of them, you may see a gamma. You're not going to see a lot of gamma, but you may see some. Now, I'm not going to draw all these, but we are going to talk about what quadrant they're in. So pi over 4, it's going to fall between 0 and pi over 2, so it's going to be in quadrant 1. 5 pi over 4, is it going to be between 0 and 1/2, 1/2 and 1, or 1 and 1/2? Well, it's going to fall between 1 and 1/2, so it's going to be in quadrant 3. All right, beta here, negative 3 pi over 4. Well, the negative means we're going to go clockwise from our initial position. So our initial ray is here, and we're going to go back this way. So we go from 0 to 1/2, 1/2 to 1, 1 to 1/2, and 1/2 to 2. So where in there would it fall? Well, negative 3/4 is going to fall between negative 1/2 and 1. So we know that we're also going to have this one in quadrant 3. Not only that, but they are going to have the exact same side, terminal side. And gamma, 9 pi over 4. So it's going to actually be, if you look at this, 4 divides into 9 more than 2 times. So it's going to be 2 plus some. So we're going to go all the way around. So we're going to go 1/2, 1, 1/2, 2, and then we still have one more pi over 4 to go. So it's going to be right there in quadrant 1 as well. And you don't have to get a protractor out to measure these, just estimate about where they are and mark the angle. So for instance, if I had done the negative or the 9 pi over 4, I'm going to go ahead and draw that one just so you see what it would look like. Of course, there's my initial side, and there's your vertex, and you're going to sweep through the whole thing and then back over, and it's going to be about right there. Now, just to clarify, what I would probably do, just to make sure that everybody understood what went on, I would do this, and that's where I would do my gamma. And I would actually mark that angle as gamma, just to clarify it. All right, now, we talked just a second about coterminal angles. We had 2 sets of coterminal angles in that last example once we draw them out. What that means is they share the same terminal side. Co, meaning shared, coterminal is, well, terminal. So they're shared terminal side angles. Increasing or decreasing the degree measure of an angle in standard position by an integer multiple of 360 degrees, otherwise known as 2 pi, results in what's called a coterminal angle. Thus, an angle of theta degrees is coterminal with angles of 0 degrees plus or minus 360 degrees times k, where k is any integer. 0, 1, 2, -1, -2, any of those. The reason why is that when you multiply the 360 by some integer k and then add it to that theta, all you're doing is you're adding a rotation. So for instance, with that last one, remember we had the 9 pi over 4. We went all the way around the circle and then came back pi over 4 more, and that got us coterminal with that original example of positive pi over 4. Now, in radian measure, increasing or decreasing the radian measure of an angle by an integer multiple of 2 pi results in a coterminal angle. So once again, an angle of theta radians is coterminal with angles of theta equals plus or minus 2 pi k, where k is some integer. It cannot just be any number. It has to be an integer. 0, 1, 2, -1, -2, -3, etc. It can't be just some random number of 4 halves. Okay, it could be 4 halves. Never mind, that's an integer. It couldn't be 1/2 or 3/4. All right, so assume that the following angles are in standard position. Find a positive angle less than 360 degrees that is coterminal with each of the following. So if we're looking for an angle less than 360 degrees and we have 420, we know we're going to have to subtract. We're only going to add or subtract 360 degrees from a degree measure. So to find this one, we're going to do 420 degrees minus 360 degrees, and that's going to give us a coterminal angle of 60 degrees. There's my angle. Now, if we had part B, we've got negative 120 degrees. That is not, it's not positive, so we've got to get it back positive, so we're going to add 360. If we add 360, we're going to end up with 240 degrees as our coterminal angle. Now, coterminal angles can be found with pi, with radian measures, by adding or subtracting 2 pi. Now, in this case, you're going to have to deal with fractions a lot of times. And remember, if you're dealing with fractions, the only way you can add or subtract is if you have common denominators. Okay, if you do not get common denominators, you are going to get the wrong answer. So for instance, with the first one here, 17 pi over 6, 17 pi over 6, we're looking for a positive angle less than 2 pi. 6 goes into 17 almost 3 times, so definitely more than 2. So we're going to subtract 2 pi. Now, I'm going to think about that in terms of 6's, so I'm going to multiply top and bottom by 6. I'm going to think of that as 2 pi over 1. So you end up with 12 pi over 6, and then you can do your subtraction, and you're going to get 5 pi over 6. Now, same thing here with the negative pi over 12. Remember, you want something between positive angle and less than 2 pi, so of course you're going to have to add 2 pi. And if you're talking about twelfths, then that means you're going to end up adding 24 twelfths, because that would be equal 24 pi over 12, because that's going to be equal to the 2 pi. So when you add that, you're going to end up with 23 pi over 12. And that is less than 2 pi, because 2 pi would be 25 over 12, so it is positive. So that's going to be coterminal with negative pi over 12. Now, you may have to add or subtract 360 or 2 pi more than one time. 750, if we subtract 360, we're still going to be greater than 360, so we're going to have to subtract it again. Same thing with the 22 over pi. 3 goes into 22 pi 7 times, so that's over 7 pi. So you're going to have to subtract 2 pi, subtract 2 pi, subtract 2 pi, and then you'll have something between 0 and 2 pi. So I'm not going to work those out, but understand that if the angle is big enough or more negative than, definitely more negative than 2 pi, you may have to add or subtract 360 or 2 pi multiple times. Now, the length of a circular arc. We can use the radian measure formula. This is what I talked about earlier. Theta equals S over R to find the length of the arc of a circle. And all we're doing is we're multiplying both sides by R, and we're going to get S equals R times theta. Let R be the radius of the circle and theta the non-negative radian measure of a central angle of the circle. The length of the arc intercepted by the central angle is S equals R times theta. S being, of course, the arc length, R being the radius, as it says, and theta being the non-negative radian measure. It has to be in radians, has to be in radians, has to be in radians. If you put degrees here, you've got some random number that means absolutely nothing. It has to be in radian measure. Alright, so a circle has a radius of 10 inches. Find the length of the arc intercepted by a central angle of 120 degrees. So, if we go and we write down our equation, and we start plugging things in, then we end up with 120, but remember, this has to be in radians, so we actually have to convert this first. So 120 degrees times pi radians over 180, the degrees are going to cancel out. 120 and 180 are both divisible by 60. So we end up with 2 over 3, so 2 pi over 3 radians. And that means that up here we're going to multiply that by 2 pi over 3. So we're going to end up with 20 pi divided by 3 inches. And that's going to be our arc length. Now, definitions of linear and angular speed. If a point is in motion on a circle of radius r through an angle of theta radians in time t, then its linear speed is going to be v equals s over t. S being how far it traveled, t being the amount of time it took. It's nothing more than standard velocity. Velocity equals distance divided by time. That's all you've got right here. Where s is the arc length given by s equals r theta, and its angular speed is omega, that is lowercase omega. This is actually a lowercase nu, if I remember correctly. This is lowercase omega, so omega equals theta over t. How much angle you've gone through divided by how much time it took. So that's going to give you how much, it's going to be a rate of angle per unit of time. That's what angular speed is. Linear speed is measurement divided by time. Here we're going to have degrees or radians per time, unit of time. So the hard drive in a computer rotates 3,600 revolutions per minute. This angular speed, expressed in revolutions per minute, can also be expressed in revolutions per second, radians per minute, and radians per second. Using 2 pi radians equals 1 revolution, we express the angular speed of the hard drive in radians per minute as follows. 3,600 revolutions per minute times 2 pi radians per revolution equals 7,200 pi radians per 1 minute. So in other words, it's going to go 7,200 pi radians per minute. Now, the linear speed in terms of angular speed, remember the angular speed is nothing more. When we talk about radians, we're talking about an arc that is the same length as the radius. So here with this omega, we're actually talking about the number of radii we have per unit of time. So if we want that to convert that over into linear speed, all we have to do is, okay, if I've got this many radians per time, and each radian is this length, r, then that's going to be the linear speed. So it's actually kind of easy to transfer from one to the other. All right, so a wind machine used to generate electricity has blades that are 10 feet in length. So write that down. R equals 10 feet. The propeller is rotating at 4 revolutions per second. Find the linear speed in feet per second of the tips of the blade. Now, if we know that we've got 4 revolutions per second, each revolution is what? 2 pi. So we have 8 pi per second. And what is that? Well, that's our angular speed. So that's our omega. And I can't do a good lowercase omega. So anyway, that's going to be our omega, our angular speed. And how do we find our linear speed? Because that's what they want. You got to be careful. Remember, the omega is the amount of angle per unit of time, and the linear speed is the actual length per unit of time. So that last thing we looked at, the linear speed is going to be the radius times omega. So when we plug that in, we're going to end up with 10 feet times 8 pi per second. Now, where I told you before that the radian measure has no units, this is not radian measure. It has a concept, a part that's radian, but it still has the per seconds. And any velocity that we come up with should be per second. So we're going to end up with 10 feet times 8 pi, which is going to give us 80 pi per second. So that's how fast the point at the end of this rotor right here is going to be spinning. It's going 80 pi feet for each second. That's pretty quick. I would not want to be trying to fly through that if I was a bird. All right, that's all of 4.1.